Let's solve another logarithmic function. Suppose I had to solve log of x plus log of x, 2x minus 4 equal log of 5x. So the idea here is going to be that if I can write a log on one side and log on the other side, then all of a sudden I can equate what's inside. So I'm going to use the log rule since we're adding these logs. Remember, there's a log rule that says log, the product rule, a times b is equal to log of a plus log of b. So I'm going to use this rule backwards and write this as a single log. So with that log, looks at log space down here. So I'm going to write x times 2x minus 4. And this is equal to log 5x. So because the bases are exactly the same, the only way these two log functions can be equal to each other is if what's inside of them are equal to each other. So then all I need to do is, well, let's figure out how to make these two inputs equal to each other. So I'll write that down, right? Another way of doing this is to raise both sides to the 10th. Raise this, use this as an exponent of 10, exponent of 10, and then use the inverse concept. But this is, I think, simpler for logs. So now I'm going to distribute x here to both sides, and I have to solve this, but what kind of equation did I just create? And the answer is, this is going to be quadratic. So I'm going to choose a quadratic methods. I can use the quadratic formula. Where all of a sudden I'm trying to solve this particular, function. Okay, or I could factor. I'm gonna try factoring first. So I'm gonna subtract to factor. Again, no matter what I do, if I factor or use a quadratic formula, I have to get everything to one side and equal to 0. So subtract 5x from both sides. And I get the following. Combine like terms. And now recognize that, okay, I don't have to use this at all. This is a simpler thing to solve. It's a quadratic. So the whole idea is to factor and equate both factors equal to 0. But this one, since there's no constant, I can just factor out the x. There's a result of factoring out the x. Again, it seems like I'm doing this going backwards again, and I am. But first I needed to get this expression to the other side. I did that. This is the result. And now the only way I can have a product equal to 0 is if one of the factors is equal to 0, say this one. So one of the answers is potentially 0. We'll get the other factor to be equal to 0. So I'm going to solve this and add 9 to both sides. I can now notice linear, both two linear equations I generated, divided by 2. And this is potentially another answer here. Now, you're not done here because you need to check. So this is a 2 potential answers, but I need to check. I look at this equation, I immediately notice that, remember, the domain of a log, domain of just a simple log, say b x equals y, that is going to be 0 to infinity. So, and it doesn't include 0. So this cannot be 0. It has to be greater than 0. So this answer is no good. So I generated a 0. When I solve this, that's not an answer. What about this one? Well, it's 9/2. it serves this one good. This one seems to be hidden a bit to me, so I'm gonna just check it anyway. Like maybe could I generate a negative number here? I don't know, maybe I could. So I'm gonna just check x equals 9/2. So I'm gonna get log of 9/2 plus log of 2 times 9/2 minus 4, and this should be equal to log of 5 times 9/2. So do I have an equality here? Let's figure this out. It's going to cancel here. What I have now is log of, then again, I got 9 minus 4, that's a 5. And I can see that if I apply the log rule, I can, again, using this log rule backwards, I can multiply these insides and I'll get exactly what's on the left side. So it'd be 5 times 9/2, and so there I have equality. So this checks out. So the solution, there's only one solution here. The solution is x, and the answer is 9/2 is the only solution to this. What about this one? Let's just try to solve this one. Again, same thing. I have a log on both sides, 2 logs. I need to condense it so there's just one log. So I'll use the other rule that says, hey, log of a divided by b can be expressed as a difference of logs. And what I have now, starting, is a difference of logs. So log base 2, sorry, log base 10. Oh, and I'm having a different little scenario, a change of base. So I have 2 things going on here, X. So I cannot just use this rule right now. Let me write this down. Why? Because I have 2 different bases. So this is a natural log, this is a natural log. I must as well change this to log base E. So I'm going to change this to log base E. So I'm going to go natural log, input, natural log. Okay. So this is going to be 10 here. This is going to be 2 here. Okay, so this is log base 10, so I need to put the 10 here. Now, there's something, did I need to do this? No, I didn't. Now that I'm thinking about it, I did not to do this. Why not? Because this is just a constant here. Okay, so well, let's just go with this. As I'm writing, I'm realizing, wait a minute, I don't have a variable. That makes life easier. This is just a number. So if that's the case, I can still bring this together. So I'm going to rewrite this. Do I want to do it this way? Thinking. No, here's something. I'm going to add natural log of this to both sides. Yeah, I really didn't have to do this. I might just go back to what it was before. Again, this is just a little puzzle. So I'm going to add this to both sides. You notice each time I'm trying to just release the variable, but I can only play with exponential roots or logarithmic roots. That's all I can do. So if I decide to do this away, then I can write this as a single log, natural log of 5 times 2 minus x, just like that. Still this log of base 10 of 2. And now how do I release this? Well, this is just a number. So I can write this in exponential form as, remember, this is base E. This is base E right here. So I can take e raised to this value, and then this equals what's inside the log, and here's what's inside the log. Okay, so again, I recognize this is log base e, raise it to this power. So again, I'm just going to use changing from exponent to log, or in this case, log to exponent. So again, I recognize this e. This is the input of the log, change it so it's e to the base. That's my exponent. Now, how does that help me here? Well, remember, this is just a constant. So this is just a number. I'm not doing anything to that. I now distribute, and what kind of equation do I have? It's linear. So 5 times 2 is 10. 5 times x is 5x. Okay. Divide both sides by, subtract 10 from both sides. Divide by 5, -5, both sides. And there you have it. This is the exact answer. Okay. So that's the exact answer. So what's the solution to this? It's what you see right there. So sometimes these answers can get, they're interesting looking. Again, I can clean that up too. I could distribute the 5 to both sides, and so here's how another way I can write this. Distribute the 5 to both sides. So what I have here now is maybe 1/5 e log of 2, and then when I distribute to the other side, I got plus 2. So maybe you like that look better. So again, I got -10 divided by -5. That gives me the 2 right here. And if I wanted to, I could take this now and raise it, like raise it to the power. No, I want to. No, I can't. Can't. This is not a log. See, again, I'm trying. I want to apply these log rules, but I can't. This is an exponent. So no, this is it. So if I wanted to know an approximation to this thing, so the answer here, I can come over here, and it might be a good idea to look at an approximation to this thing to see if it's even feasible. So I got -1 divided by 5. I put parentheses just to make so I'll put parentheses here. Just to, I could write that out, but and then e, and our power is log base 2, no, log base 10 of 2 plus 2. And this is approximately 1.729. I'm going to write a few more decimals. 975. Okay. Does that seem to work? Let's try it. So now let's just see if this works. Log of 2, it's simply approximately, minus, I'm going to go natural log. Well, then I'm going to enter that number. So this is not exact. So I'm not expecting exact equality, but very, very close. So when I enter that, oh, and this is 2. Insert here. Insert 2. Subtract this one out. Good. There we go. So this, when I do all this, so log is 10 of 2 minus natural log of 2 minus, and enter this number 1.7 2975, I get approximately 1.6094. Approximately. 3. What's the other side? Well, let's take natural log of 5. Natural log of 5. There we go. Yeah, that worked. That is a solution. I get the same number again. So, yeah. So this is the exact solution, which is approximately that. So the bottom line here is that, you have logs, rules of different ways you can manipulate this here. Like I started thinking, oh, wait a minute, the logs are not the same. I need to get them the same until I realized, wait a minute, but that's a constant. Had that been log of X, yes, that changes things. I would have had to do this to start manipulating the expressions, but I didn't have to. So I left it, since again, I'm just writing two symbols throughout can get cumbersome, and I didn't have to do that. It wasn't going to help me later. Like here, it wouldn't have helped. I would have had still this ratio sitting right there. I couldn't do anything with it. So knowing the rules and what you're allowed or not allowed to do kind of changes your path forward.